All right, let's start looking at some of our characteristics of our higher degree polynomials. So we know with our second degree, our parabolas, they have a vertex and they open up or they open down, right? And our vertex, remember, could be a maximum or it could be a minimum. It's pretty straightforward. Well, when we get into degree of 3 or higher, we need to pay attention to some certain things. We need to pay attention to its shape, its end behavior, the number of roots, and do they have any maximum or minimums, which in this case we call local minimums and local maximums, because there could be multiple ones, depending on which area you're looking at and what type of degree it is. So let's just take a look at our cubic, our third degree. So for our third degree equations, what do we notice about the shape of all these? Well, they all kind of make, some type of S in a way. It's like an S that fell on its side. In this case, this first one, it starts down, it comes up, comes back down like a parabola, but then it bounces back up. So it finishes on the opposite. It started from down low, finishes up high. And we have some other ones that are very similar to that. Same thing here, except this one doesn't totally bounce down low, but it comes back up. Same thing with this green one. It came up, bounced back down, and it came back up. Okay, and then we had ones that started up high, but if you noticed, same thing, they worked themselves back, and then they finished the opposite direction. Okay, same thing with this red one here, came up and finished the opposite direction. So it looks like the shape has the same type of end behavior with all these. And what do we notice about the end behavior? It's opposite from how it started. So if it starts down, it finishes high. If it starts high, it finishes down or low, right? So that's one thing that we should notice about our third degree polynomials here. How many roots would they have? Well, we kind of talked about that yesterday. If it's third degree, it should have 3 total roots. And some of them are nice and easy to see. So in this first case, my 3 roots, 1, 2, 3. They're all x-intercepts, so I know those are all real roots. Do I have any other cases where that's true? Yep, down here at this blue one. 1, 2, 3. So those both have 3 real roots, right? Because they're real numbers. There's another one that has 3 real roots, but it's kind of harder to see. If I notice this red one up here, I got 1, but then this red guy doesn't come up and above and back below. You see how it hits the x-axis? We call this a bounce, and we'll get into that in a little bit further here. But this is where there is a double root. Okay, and we'll talk about that in just a second. So there's really 2 roots there and 1 root there for a total of 3. And the same kind of case is this one. We see a root right here, and then we're actually going to have 2 imaginary roots or complex roots because it doesn't cross or bounce off the x-axis anymore. So we'll talk about that in a little bit later too. And then this last guy, same thing. You got 1 root, and there's going to be 2 complex roots, 2 roots that are not real. And the one thing that we know about these 2 is that they're going to be conjugates of each other. And we'll talk further into that too. And I proved that back in our section 5 notes when we looked at complex numbers. When I did that one on the parabola, they're always conjugates of each other. Okay, they always get 2 roots that are conjugates if they're complex. Oh, and let's take a look at our local maximum and minimums. And if we notice, some have local maxes and mins, some don't. So have a look at this first guy. You got a local max and a local min, right? There's a local max and a local min. If I look down low, now I got a local min, then a local max. This next one's kind of tricky. There isn't any local min or local max. Sounds a little different case. Whereas in the rest of these, local min, local max, local max, local min. So we're just looking in specific spots if they have any maxes or mins. And then we also have 4th degrees, our quartic, we like to call them. Quartic shape. So shape and the end behavior. If you take a look at the shape and end behavior, now they start and end the same, don't they? So in this first guy, it started down low, right? Started in the negative direction and it finished in the negative direction. The next one, it started from the positive direction and finished in the positive direction. Okay? And if you notice, degree 4, that's an even number, right? And if I look at the one previous, that was an odd degree, right? And they finished opposite ends. Okay, that's something that we should start noticing. And roots, how many roots should they have? They should have 4 roots. Well, let's look at the obvious ones that have 4 roots. Down at this green one, 1, 2, 3, 4. They're all real, all x-intercepts. Do I have any other of those cases? Yeah, this red one, 1, 2, 3, 4. Nice. Okay, what about these top 2 guys? This orange one. If we notice it has a bounce, so that's going to be a double root, which we'll talk about in just a second, and another bounce, right? So that's another double root. So 2 roots here, 2 roots here, for a total of 4 roots. Same thing with this purple one. We got a bounce, that's a double root, so 2 there, 1 here, 1 here, 4 total. Okay, this last one gets a little tricky. Here's a root, and then we call this a terrace point, and we'll talk about that in just a second. Whenever there's a terrace where it like levels off for just a bit, see how it kind of levels off there? That's a triple root. Okay, and I'll show you how we can all represent those in just a little bit. But they all have 4 roots, right? Triple root would be 3 plus 1 for a total of 4 roots. So they all have 4 roots. And local maxes and mins, okay, now they could have up to 3 local maxes and mins. And the same type of thing. Let's just look at this first one. We got a local max here, a local max here, and a local min there, okay? They're just kind of like the vertices of, or the vertices of like the little parabolas that happen throughout in a way. Okay, and if we look at the kind of the shape, they almost make like, you know, an M shape or a W shape. That's kind of the shape that they get for a degree 4, a quartic. And let's just look at a 5th degree as well. We should be getting used to it now. They're going to end opposites, right? Starting the ends are opposites. Start as opposite the end, right? If we should notice that it's an odd degree. If we look at the roots should be the exact same as the degree, so it should have 5 roots. And, you know, in some cases they're kind of tricky. Like here's a double root, triple root, so 2 and 3 for a total of 5. Down here you got 1, 1, 1, 1, 1. So they're all real. You know, sometimes they're imaginary. I don't think I have an imaginary here, but some are double, some are triple roots, and we'll explain that here in a second. Same thing, local maxes and mins. You could have up to, 4 total now. So you can't have as many as the degree, but it's always like 1 less than degree for the local maxes and mins. 1 less than the degree. All right, so if I look down like this blue one, got a local max, a local min, a local max, a local min. I could never have 5, but I could always have 1 less or smaller than that. Okay, so the thing that we noticed, end behavior. Even degrees start and end the same. Right, so we could have a parabola. We could have a 4th degree. Okay, things like that. Odd degree, start and end opposite. So a 3rd degree and a 5th degree. Okay, they're always going to end opposite. That's something that we realized. Another thing we realized is the degree number equals the root number. Okay, some roots are real, and those you can see are the x-intercepts. And we'll talk here in a second about the double and triple roots. But then some are also imaginary. All right, you cannot be seen. They're not x-intercepts. But the nice part is they always occur as conjugate pairs. That's important. Okay, so if you have an imaginary root, a complex root, if you had a complex root of, let's say, 3 plus 3i, we also know that there'd be another root of 2 minus 3i. It's conjugate. Okay, so that always occurs on all polynomials whenever there's complex roots. So don't forget that. That's a big, important rule for us. All right, and so like we talked about, there could be double roots. So for double roots, we want to look for bounces. Look for bounces. So for example, you know, I don't know the scale factor in this case, but if I wanted to write the factored form, I notice it has a root at 2, so I could say x minus 2. And then it has a double root at 5 here, or a bounce. So I'd say x minus 5 and another x minus 5, or I could write it as x minus 5 squared, right? So a total of 3 roots because this would be a degree 3. Okay, well, the same thing with this one. If I notice it starts down and it ends up, so it's got to be an odd degree. So what do you think? Is this going to be 3 roots, 5 roots, or 7 roots? Well, let's take a look. This looks like a solid root here, right here, right here, and here we have a bounce. So there should be 2 roots there. So when I write this guy, when I write this root, I don't know the vertical stretch here, but I would say that as x minus negative 4, x plus 4, and it'd be squared because it occurs twice. And then I'd put the rest of them, x plus 1 for this guy, and then x minus 2 and x minus 3. That should be a 3. Okay. And then there's also triple roots, right? That's where we're looking for terrace points. Okay, so bounces for double, terrace for triple. So if I look at this left one, here we have a bounce. So there's 2 roots. And here is a terrace point, right? So there's 3 roots there. And there's no other spots that it crosses. And let's see, it started up and it ended down, so it's got to be odd. I'm guessing it's going to be a 5th degree, right? 2 roots, 3 roots for a total of 5. If I wanted to write this in factored form, I don't know the vertical stretch yet, but I could say x minus negative 4, x plus 4 for this bounce, and that's squared because 2 roots are occurring. And then here we have a x minus 2, right? And that's cubed because it's a terrace. It occurs 3 times. That root occurs 3 times. That's the trick there. Okay, same thing here. We got a triple root right here. And the single root. So 3 roots, 1 root. And it looks like it should be an even degree because it started from the positive and it ended in the positive. So this should be a degree 4. So that works out, right? So what we're noticing is that if we're given the roots and a point that it goes through, we should be able to write its equation. Because, like in this case, when I'm given a point, I need to solve for that a, that vertical stretch right there. And remember, the point can't be one of the roots. It cannot be one of the roots. Let me repeat that one more time. The point you plug in cannot be one of the roots when it's in factored form. If you're in vertex form, that's totally fine, or in general form, but not when you're in factored form. And then what are the connection between the roots and the factors? Those should also be the same, right? The number of factors and the number of roots should always be the same. And they should also match what? The number of the degree as well. Okay, those are all the same. The number of factors, the number of roots, the number of the degree, they're all the same. So let's write an equation. So we say y equals, always account for the vertical stretch. I'm going to leave the a there since we don't know it yet. And roots of 3, so I'd say x minus 3. A root of 1, so x minus 1. And a root of 4, negative 4, so x minus negative 4, which is really x plus 4. Okay, it doesn't say that any of them occur double or triple root, so they're just like that. And then to find what the a is, we have to plug in a point that's not a root. Well, the only point we know is the y-intercept at 36. That'd be the point 0, 36. I plug in 36 for y and 0 for x, and we end up with 36 equals a times negative 3 times negative 1 times 4, which gives us 12a, so a would be 3. So all I would do is replace the a with 3, and there's my equation right there. If I wanted it in general form, I would expand that whole thing out. Okay, but we'll do that on the next one. And just like we talked about previously, if you have a complex root, know that the conjugate of that is also a root. Okay, so the conjugate is also the root. That's something important. Let's do one of those just so we get that down. So if I look at this case here, write the equation in general form. So we're going to expand it out at the end here. So I should say y equals a, and then our roots. So we have a root of 3, so x minus 3, and a root of 4 plus 2i. Well, 4 plus 2i, how does that work? We always write x minus the root, 4 plus 2i. But I also should have its conjugate as well, so 4 minus 2i. So even though they don't tell you, that's also one of the roots. It's always one of the conjugates. So I'd say x minus 4 minus 2i as well. Okay, in this case, I don't know any other points on there, so I can't even solve for the a. So we're just going to assume that a is 1 in this case. So now I'll say y equals So I got x minus 3, and I'm going to simplify this. So I got minus 4 minus 2i. So I got x minus 4 minus 2i, and then I got x minus 4 plus 2i. And then I got a long distributive process here. So